Jai Hind everyone, I am Dr. Nitisha Shrivastava, Assistant Professor in the Department of Electrical and Electronics Engineering, Akgec Engineering College in Ghaziabad in Uttar Pradesh in India. Today we will discuss some of the basics of constructing a Bode plot. This topic is a part of control system, and this Bode plot is basically the frequency response plot to assess the stability and the performance of the system for different frequency ranges. So, what are the basics? Like sinusoidal transfer function are commonly represented by a Bode plot. It is a plot of magnitude and angle of the transfer function. So, we will be plotting both magnitude and angle of the transfer function against the frequency. So, the x-axis will consist of the frequency term, whereas the y-axis will consist of the magnitude and the phase. It is a logarithmic plot and consists of two plots. Plot of logarithmic of magnitude against the frequency in a logarithmic scale. So, frequency is on a log scale, whereas the magnitude will be on a linear scale. And the second plot is the plot of phase angle against frequency in the logarithmic scale. So, here also the frequency is at a log scale, and whereas the phase is in a linear scale. Logarithmic magnitude is represented as 20 log Gj omega. The base of the logarithm is 10 and the unit is decibels, usually abbreviated as dB. So, if we have a simple example like Gs is equal to 1 upon S plus 1. So, if this is the transfer function given in the S domain, it means that we are talking about logarithmic magnitude is represented as 20 log Gj omega. It is 20 log Gj omega. It means that we are substituting S with J omega. So, our transfer functions become Gj omega is equal to 1 upon J omega plus 1. Since it is the plot of frequency versus magnitude and frequency versus phase. So, in place of S, we write J omega. Some of the basic terms involved to construct a Bode plot. Now, to construct a Bode plot, in Bode plot, we have certain basic terms and the rules to draw the Bode plot for different terms involved in a transfer function. Now, like we have a simple transfer function as mentioned in the previous slide, Gs is equal to 1 upon S plus 1. So, that means we have one constant term here and we have S plus 1 in the denominator. So, these are the terms, or if you have a transfer function of the form Gs is equal to S plus 2 upon 1 plus S, and you have a gain factor 100. So, the transfer function may involve various different factors, and we are going to understand here how do we plot the magnitude and the phase for individual different terms. Like we will start with the first one. If you have a constant term in the transfer function, that is K. So, how is K represented? Constant term K, it gives a constant magnitude whose value will be 20 log K, and it does not give any phase shift. It is represented by a line parallel to the 0 dB line. So, this y-axis is in dB or you can also write it in the small dB. This is the magnitude and this is the phase. This is the factor we are talking about. This is the magnitude and this is the phase. So there is no phase shift and therefore this will be a 0 degree line. And then where does it starts from? Slope of 0 dB, since it's a straight line, so the slope is 0 dB per decade and it starts from a point having a magnitude 20 log k. So this is for the constant term k. Now the system may have a pole or a 0 at the origin or both. Now we have, if we have the term s square in the numerator, if we have a function gs is equal to s square in the numerator. So it means that there is 2 zeros at the origin. Or if you have a function 1 upon s square, that means this transfer function is having 2 poles at the origin. So the factor what we are considering here to draw the magnitude and the phase plot for this particular factor is substituting that s with j omega. So substituting s with j omega means here, if n is equal to 1, that means it is j omega. If n is equal to 2, that means it is j omega square. So it means that this n represents the power of s in terms of 0 in the system. Now regarding the poles, if you have 1 upon s, that means n is equal to 1 here, and if you have 1 upon s square as the transfer function, then in this case n will be equal to 2. So this n represents this. Now it is a magnitude of 20 log omega. The magnitude will be 20 log omega and it is a straight line having a slope of plus or minus 20 dB per decade and passes through omega is equal to 1 radian per second, whereas its magnitude is 0 dB, where at this point when omega is equal to 1, this is the omega, that is the x-axis frequency line, and in case of 0, it is a rise in the 20 dB per decade, that means plus 20 dB per decade. And in case of a pole, it will be pole at origin. We are talking about the 0 at origin or the pole at origin. Now when there is a pole at origin, then it will be minus 20 dB per decade. The slope is minus 20 dB per decade and the magnitude at omega is equal to 1 will be 0 dB. That is, when omega is equal to 1 radians per second, at that point its magnitude will be 0 dB per decade. And here 20n, n represents the number of zeros or number of poles. So if n is 2, now in case if n is 2, that is 20 into 2, it becomes 40 dB per decade. So if there are 2 zeros at the origin, then it will be 40 dB per decade, and if there are 3, it will be 60 dB per decade rise, and similarly if there are 3 poles at the origin, then it will be minus 60 dB per decade. And in case of phase, when we plot it in the phase will be here as constant value 90n. Again, if n is 1, it will be a constant line of 90 degrees, and if it is n is 2, now if n is 2, then we will have a constant line of 180 degrees. The next term is a simple pole or a simple 0 at the origin. Simple pole or simple 0 means 1 upon st. 1 upon st is the standard form in which we write the transfer function to sketch a Bode plot. So 1 plus st, this is a 0. If we are talking about the numerator, we will have at 1 plus st raised to plus n, and for a pole it will be 1 upon 1 plus st raised to n. So n again here is the square or raised to 3 or raised to 4 and so on. So the term, if we are having, if the transfer function is having a term of simple 0 or simple pole, then the magnitude is given by n into 20 log 1 plus j omega t. So the magnitude is given by this expression, and it is having a slope of plus or minus n into 20 dB per decade. So how are these asymptotes approximated? Asymptotes are approximated with the two cases. If omega t is less than 1, we are talking about this 1 plus j omega t. If this omega t value is very, very less than 1, then the term will be neglected. So in that case, log 1, n into log 1, it will be 0 dB. Whereas when omega t is very much greater than 1, then the magnitude is this value, plus minus n into 20 log omega t. So this factor we have considered for the two cases, considering the value to be very much less than 1 and very much greater than 1. So it has a slope. What about the slope? Slope is plus minus n into 20 dB per decade. So n again stands here for this term. So just to understand, what could it be? If you have 1 upon s into s plus 2 raised to 2. So this n stands for this particular value. Now, what is this corner frequency where the slope changes? So this is found out by the simple value omega t we consider as 1. So that means that corner frequency omega is equal to 1 upon t. And what is t? It is this part, that is the coefficient of s. So this omega is called the corner frequency, and due to approximation, maximum error at the corner frequency is 3 dB per 3 dB magnitude. So the three terms involved are constant k, then a pole or 0 at origin, and then simple pole or a simple 0. The other factor which would come, so how do we plot this? We will understand this. So if you have this term 1 plus j omega raised to n, it is nothing but this value 1 plus st raised to n. So we are taking the it into the denominator. So this z is, we are mentioning here, this is the corner frequency. So this corner frequency in this case is marked here, and the rise in the slope is 20 n dB per decade. So as mentioned here, the slope is, it has a slope of plus minus n into 20 dB per decade, which means that this is that rise in the slope. And in case of 0, it is, the slope is minus 20 n dB per decade. So these slopes, when we talk about in the phase plot, this is for the phase, this is for the magnitude, and this is the factor we are considering. So this z in terms of phase plot, we will mark this point z by 10. So, for example, we have 1 upon s plus 2, right. So, when we write it in the st form, we take that 2 outside. So, this becomes s by 2 plus 1. Now, this is nothing but 0.5 divided by 1 plus s by 2. So, in place of s, if I write j omega, this becomes 0.5 divided by 1 plus j omega by 2. So, what is my p here, since this is a denominator part? So, it means that my p here is, when I compare it with this becomes in the denominator 1 plus j omega upon p. So, raised to n. So, we don't have any square or cube term. It means that it is simple 1. So, n is 1. So, what is my p? P is basically 2. So, that means when I mark here, this p will be 2 by 10, that is 0.2. So, that means the frequency I will be marking it as 0.2, and till 0.2, that is p by 10, the value will be 0 degrees, whereas it will be minus 90 degree or minus 45 degree per decade. How it is like that? Now, when I go from here and till this point, we can see that this is the slope here. So, 10p is nothing but 10 into 2, that is 20. So, from 0.2 till 2, that is 0.2 till 2 is 1 decade, and fine. So, 0.2 till 2, and this is 1 decade, and then from 2 to 20, this is the next decade. So, this is 2 decade, and you can see that it goes till minus 90 degree. This is 0 degree and this is minus 90 degree. So, it means that from 0.2 to 20, it is 2 decades, and this is 90 degree. This is 90 degree. So, that means this part is 90 degree and this is 2 decades. Therefore, per decade it will be 45 degrees. So, per decade it will be 45 degree per decade, the slope is. Similarly, we plotted for the factor in case of zeros. This is about the simple zero and simple pole. We could also have a term of the second order, that is s square plus 2 zeta omega n s plus omega n square. So, in this case, the zeta is considered for the two conditions. When zeta is greater than 1, it can be treated as 2 first order factors, and if zeta is less than 1, it's an underdand system. The magnitude is plus or minus 20 log. When I rearrange the terms for the term s square plus 2 zeta omega n s plus omega n square, when I rearrange the term, I get the magnitude as this, and this is the real part and this is the imaginary part. So, the magnitude will be under root the real square plus the imaginary square. So, this term is approximated by two straight lines. Again, we are considering the corner frequency, and what is the value of the corner frequency? The value of the corner frequency is omega n. Below the omega n line, it follows the 0 dB, and beyond omega n, it will have a slope of plus or minus 40 dB per decade. For a simple pole, it was plus or minus 20 dB per decade for one simple pole and one simple zero. Now, if the pole is repeated, or if the pole 0 is repeated, we have the term n there. Now, in this case, it will be plus minus 40 dB per decade. Error due to approximation depends on the value of zeta. If zeta is small, then the error will be large. So, how is this represented in the Bode plot? This is the factor we are talking about. So, this could be a second order value in the numerator corresponding to the zeros, and for this it is corresponding to the poles. So, this is the magnitude plot and this is the phase plot. So, here we can see that till omega n the value is 0, omega n is the corner frequency, and there is a rise 40 n dB per decade, and in case of a phase it is going to mark here as omega n by 10, and till then the value will be 0 degrees, whereas till here this part it is 10 omega n. So, it is 180 degree, it goes till 180 degree raised to into n. So, this will be 90 degrees per decade slope, and this is a fall of minus 90 degrees per decade slope. So, this is a phase plot in general. If the transfer function is given by this, then how is the phase represented? For this S, when we substitute into j omega, it becomes minus 90 degree plus tan inverse omega t1 and minus tan inverse omega t2 minus tan inverse. This is for the second order system. As we can see, this is the real term and this is the imaginary term. So, that is what has been mentioned here. The slope will change at this is the point which should be considered when you construct a Bode plot. The slope will change at each corner frequency by plus 20 dB per decade for a simple 0 and minus 20 dB per decade for a simple pole. And for a complex 0 or a complex pole, it is for 0 plus 40 dB per decade and minus 40 dB per decade for a complex pole. So, these are certain advantages of the Bode plot, and plotting the Bode plot is relatively easier as compared to the other methods, as the loci of these terms can be represented by straight line asymptotes, as we see that it is the slope changes at the corner frequency. All the multiplication is converted into addition. That means simple expression gs upon is equal to k upon this, and we can convert it into the addition and subtraction terms. And the low and high frequencies characteristics can be represented in a single line diagram. Therefore, it is easier to analyze the stability of the system looking at the sketch of the Bode plot. If modification of any existing system is to be studied, it can be done easily on a Bode plot. So, these are the basic part of Bode plot, where we have discussed the plotting of different terms involved in sketching a Bode plot, and also discussed the advantages of the Bode plot. Thank you.